So yesterday morning, Frederic showed some results of eigenvalue problem computation. And so I think we mentioned this a couple of times during the talks since yesterday, but there are basically two ways to solve eigenvalue problems in PETSI, in FreeFEM, sorry. One of them is through let's say, legacy API, which is called the eigenvalue. So there are some examples on the distribution for the for this, which are under examples eigen. Okay, so for example, a lap 3D eigenvalue. And so you'll see some calls with eigenvalue. Okay, and so this, whenever you see this kind of call, it means that FreeFEM is calling the RPAC library. So RPAC is a quite old software. It was developed like in the 80s, 90s. And so there is not much maintenance since at least a decade. And so there is a new package which is called RPAC NG, which is an up-to-date, let's say, implementation of RPAC. But yeah, and so anyway, the algorithm under the hood is still the same in the sense that it's a Krylov-Shor method. And so the Krylov-Shor method is a very powerful method for eigenvalue problem, but you don't have much flexibility in the sense that, for example, you cannot try new methods for solving eigenvalue problems, like the power method, like Jacobi-Davidson method, and so on and so forth. And so there is another approach in FreeFEM for solving the eigenvalue problems through SLEPC, which is a much more modern way, let's say, of solving eigenvalue problem. And so SLEPC is a sister library of PETSI. So PETSI was initially mostly developed in the US. So now there are developers a little bit in Europe, in Saudi Arabia. SLEPC, on the other hand, is mostly developed in Europe, and so mostly at Valencia in Spain. And so it's tightly linked with PETSI. And so we can access SLEPC through FreeFEM via the PETSI plugin. And so maybe we can... Yes. I don't know. So yeah, so one of the let's say weak point of the eigenvalue API in FreeFEM, in my opinion, is that there are some parameters that it's difficult to understand. So for example, why is NCV and maxite 0 here? I can't tell you. There is also something like mod, which is I'm not sure it's explained somewhere, so you need to. Mod is explained. Okay, but. Okay, largest. Yeah, sure. So I don't know why NCV is equal to 0. NCV is about internal basis number. Yes, but it shouldn't be 0. That is default value. Default is set by 0. Yes, but internally it's not possible to be 0. So why? Maybe we have to look up the code. Yes, yes, and so it's not very user friendly in my opinion. Okay, visible. Visible. What do you mean? I think my screen is sharing. Visible. Okay. Anyway, so what we could try maybe is to start with an example in FreeFEM, in plain FreeFEM using eigenvalue, and then we transition to SLEPC. And so again, it's mostly for visualization purposes. I prefer to do things in 2D because we have access to FFGlut and whatnot, but everything works in 3D, meshes, meshel, and so on. Also because for computational purposes, it's lighter in 2D. But for example, I think lap eigenvalue is not too difficult to. Okay. So this is another prime example of why the eigenvalue API is not ideal. So for example, when you solve an eigenvalue problem, x equal lambda bx with a shift, the shift should never be in the bilinear form. It should be something which is specific to the eigenvalue solver. And so it's the duty of the eigenvalue solver to compute A minus sigma B. It's not the duty of the user to do this. And so currently in the FreeFrame interface, I don't know why that is, but the shift is inside the bilinear form. And so that's not okay. But anyway. Yes, but again, it's not the yes, but it's not the job of the user. But anyway, so we take this piece of code. So let me tack. So tack Friday. So we do CP repo FreeFrame source example no eigen, and so the name is lab eigen. Hop. Okay, so first let's check that everything is running okay. FreeFrame++ lab eigenvalue, no verbosity with graphics. Okay, so these are the eigenvalues of the Laplacian on the square. Perfect. Okay, so I will do some very basic editing. So first again, so here in this scenario, sigma is equal to 0. So it's not very a big deal to put the minus sigma 0. But again, it's not the duty of the user to put this in the bilinear form. Okay, it's using P2. Let's go back to a verbosity of 0. We assemble everything. Okay, okay. So another point which is important to keep in mind here is the boundary condition. And so this is a little bit technical, but again, I don't like this remark because we are using a TGV of 10 to the power of 30. And so take directly boundary condition on A, but not on B. And so this can be quite confusing to the user. And so in fact, we can use two kind of TGV. The TGV that we will use will make it possible to use the same Dirichlet boundary condition. So here, I will just use the same boundary condition. Oops, sorry. And so instead of using TGV equal 10 to the power of 30, which in my opinion is not the most practical way of doing Dirichlet boundary condition, is to use two values. So here we have a symmetric problem. So for the first matrix, we can use TGV equal -2. And so we want to impose the proper Dirichlet boundary condition. Why the square bracket? Or we can remove those, actually. They are not very important. So the square bracket are mostly for problems. So the square bracket are for vectorial finite element space, and the angled bracket are for composite FE space. But for purely scalar problem, the brackets are not necessary, but they don't hurt. Actually, I think we can also do this. I'm not sure. I will double check. Yeah, so if we put TGV equal -2 on A, we need to be careful about the Dirichlet boundary condition on B. And so we, in fact, need to nullify the rows associated to the boundary condition on B. And so to nullify the rows and the columns on the matrix B, we can use another TGV value, which is -20. Okay, so this is something which it's a little bit documented. I think it's documented in a tutorial, But anyway, I will go back to the tutorial. If we look at penalization, okay. With TGV equal -2, we have this matrix, and with TGV equal -20, we have this matrix, but with a 0 block instead of the identity matrix on the last block. And the same with TGV -1. With TGV -1, we have this matrix. And with TGV equal -10, we have this matrix, but with a 0 block instead of the identity block on the lower left corner. And so this is important to impose the Dirichlet boundary condition. Okay, and that way we don't need to use 10 to the power of 30, which can be quite bad when it comes to solving problems iteratively. So either linear systems or eigenvalue problems. Okay, so then we set some parameter, and I will make sure that everything still runs perfectly fine. So I go in Friday, and then I run fm++ lab. Token. Okay, so no, we cannot use this for composite FE space. Not sure why, but let me. Okay, so we still have the same eigenvalue. We just changed the TGV for now, which is not really a big deal. So now the real question: how to solve this problem with PETSI? So sorry, how to solve the problem with SLEPC. So to solve the problem with SLEPC, we first need to load the. There was initially a SLEPC plugin. But now this plugin has been absorbed, let's say, in the PETSI plugin. So you can directly load PETSI. And this will load both SLEPC and PETSI. Okay. And so now keep in mind that whenever you do load PETSI, you need to run FreeFM++ MPI instead of FreeFM++. But it should just run the same. FreeFM++ MPI. And so we still have the same. Okay, perfect. Oops, sorry. So when you want to solve eigenvalue problem with SLEPC, instead of using FreeFM matrix, we will need to switch to PETSI mat. And keep in mind that a mat in PETSI can be very abstract. Okay, so you can use an assembled mat. You can use a mat shell when you only have the action of the matrix on a vector. You can solve eigenvalue problem with a hierarchical matrix. For example, if you have a mat assembled from a BEM variational formulation, and so on and so forth. So in this example, I propose that we do it 2 ways differently. The first one will be through a simple conversion of the matrix to assembled mats. Okay, and so as I showed yesterday during the presentation, we can very easily convert the matrix into a mat using the copy operator, let's say, that I will just show now, which is simply C takes as input parameter the FreeFM matrix A. Okay, and we can do the same for B, mat B. mat D, which take as input parameter the matrix that we want to copy inside the PETSI mat, and so we have B here. Okay. And so just as for the linear solvers, we try to make the interface as interoperable with the basic eigenvalue API. And so in practice, we should be able to do something like int kk equal. And so instead of eigenvalue, it will be EPS solve. And so for the moment, I will just do a simple solve with no additional parameter. Okay, and so let's see what we get now. I just want to make sure that the code runs. It does not, so that's fine. Ah, yeah, of course. So here we can see that I'm trying to call EPS solve with matrice creuse, which are the FreeFM matrix. And so FreeFM is telling us that we cannot use a pair EPS solve with 2 matrix creuse. We need to use EPS solve with either 2 PETSI mat if we have a generalized eigenvalue problem, or a single PETSI mat if we have a standard eigenvalue problem, or a PETSI mat and a polymorphic operator. So polymorphic operator are basically func when we want to just give the action of a function on a vector. I got the name wrong. It's not A, it's C, and it's not B, it's D. Okay, I can see that I have some error. Let's try to figure out. Okay, and so the error are that there is some pivoting. Okay, so the problem is indefinite. I'm not sure why. Okay. J'ai pas compris. Moins 20? Là, je pense qu'il est en train d'inverser B. Parce qu'on fait.
Tout seconde. On peut changer l'appel de commande de FreeTend dans VS Code sous Windows parce qu'il y a une erreur.
C'est compliqué de changer l'appel en live, malheureusement, il faut republier les tronçons, c'est chiant.
Bon, c'est pas grave. On fera ça après. Merci.
Yeah, so a little bit of PET-C debugging, SLEP-C debugging. So we have an error here. And so we need to figure out why we are trying to do the pivot, why we are trying to invert a system with zero pivots. In practice, we are not supposed to have a zero pivot because we want PET-C and SLEP-C to invert A, which is supposed to be a positive definite. And so we can have a look at the back trace. And so the back trace tells us that there is an issue when setting up a shift spectral transformation. And so this is the issue. If we do a shift spectral transformation with a zero shift, we are doing a factorization of B. And so we want SLEP-C to do a factorization of A. Okay. And so instead of using a shift spectral transformation, we need to use a shift and invert. So basically permute the roles of A and B. So this is a little bit technical. Hopefully, the SLEP-C manual, so SLEP-C, the SLEP-C manual is quite well written. And so if you are interested and want to know better all the technical details of eigenvalue problem, you can have a look. And so in particular, there is a full paragraph, if I'm correct, on the spectral transformations. Spectral. The videos? Yes, there are also videos. That's right. Okay, so instead of doing a shift spectral transformation, we want to do a shift and invert. And so we can do, I think, ST type S invert. Okay, and so now no error. Of course, we still need to check whether the solution is correct or not. So this is still the RPAC eigenvalues. And so now, okay, maybe first we can use some common line arguments to check the result, and then we'll see how we can fetch the result directly inside the FreeFEM code. So first, I want to make sure that the convergence of the eigensolver is okay, and that SLEP-C is not giving any error, and things are converging appropriately. So just as yesterday, when we did like KSP view, KSP converge reason, the syntax is very similar. SLEP-C is really a sister library of PET-C, so the lingo is the same, the way of parameterizing the solver is very similar. And so here, for example, we can do EPS, so we are solving a linear eigenvalue problem, so all the prefixes start with EPS, and we can do EPS converge reason, for example. Okay, and so we can see that, in fact, everything is going according to plan. The linear solver is converging because we have reached the desired tolerance and we are converging in a single iteration. So here we are just asking for a single eigenpair. So of course we can ask for more eigenpair. Again, for now I'm doing everything with the command line, but afterwards we will shift to the .edp script. And so for example, we can ask more eigenpairs using the EPS NEV. And so for example, we can ask for 10 eigenpairs. Okay, we can see that now things are converging properly, but it takes slightly more iterations, so we are converging in 3 iterations. Maybe we want SLEP-C to check that the error is appropriate and that we are not computing, let's say, wrong eigenvalues. And so for this, we can check also the error. So yesterday we saw KSP view final residual. And so with the EPS, we can do roughly the same. So EPS view, I think it's relative errors. Let me just check a sec. Tac. No. Okay. Error relative. And so we want SLEPC to be slightly verbose. And so we will put info details. Non. Non plus. Il n'y a pas de S. E. Ah. Bah alors. Ah, juste, okay, sorry. Okay, sorry. So there are some little twists. Okay, perfect, thank you. And so what now SLEPC does is basically compute x minus, so x is the eigenvalue, and k is the, x is the eigenvector, and k is the eigenvalue. And so for all the k's, it computes the difference and prints the error. So everything is okay when it comes to error analysis. Tac. And so now it's interesting because we can check the result against what RPAC is producing. And so we see that the lowest eigenvalue is 2. With RPAC, we get 2. Then we get 5, 5, 5, 8, 10, so on and so forth. So the eigenvalues are matching. So it's quite positive. Of course, you can leverage the flexibility of PETC and SLEPC. And for example, if you want to post-process your eigenvalues in MATLAB, you can do something like EPS view values, ASCII, and then ASCII MATLAB. And so it will automatically dump for you the eigenvalue that you can then import inside MATLAB. You can do the same for the vectors. Of course, it's a little bit more verbose, but you get the idea. Okay, so it will dump all the vectors for each. Yeah. If you have a lot of degrees of freedom, it's painful, but you get the idea. Okay, so maybe just for good measure, we want to check what is being done internally. And so we can do this with EPS view, just like we did KSP view yesterday. And so, so for the details of the EPS solver, so there are a lot of details, but yeah, by default, we do a Krylov-Shor solver. It's using a thick restart method like in RPAC. We are looking for the eigenvalue which are closest to 0. We are computing 10 eigenvalues. So the famous NCV of RPAC here is 25. So again, these are quite technical details. You can try to fine tune them, but there is in practice no real need for easy problem, let's say. If your problem is very ill-posed, you may have to adjust some of those parameters, but by default it should work. It should work well. Okay, so we are doing indeed a shift and invert spectral transformation. And so when we do a shift and invert spectral transformation, we need to factorize a linear system or to solve a series of linear systems. And so here by default, we use an LU factorization for solving each of the linear systems. But I think you can do something different. I will check, but for example, instead of using an LU method, we could do something like use a GMRES for the linear solver. So something like FGMRES and then SPC type hyper. I think this should work, and then we do a PS monitor. I'm actually not sure it will work, but we can try. Tac, it does work. And so we get exactly the same eigenvalue. And so tac, it's converging in the same number of eigenvalue solver iteration. And if we want, we can have the number of inner linear solves by using ST KSP converge reason. And so here we will see that each of the eigenproblem solver iteration requires a series of multiple linear solves. And so we can see that, so in fact, the number of linear solves is dependent on the NCV parameter that we showed before. So it's a little bit technical. Again, this is like a block iterative method. So it's a little bit technical, but basically you can fine tune the solver that you use inside the iterative solver. Okay. So what's the size of the problem? Okay, the size is not too big. So in fact, if you are not too sure of what you are doing, you can go back to the good old LAPACK. And so, for example, you should be able to do simply EPS type LAPACK. Wait, why is it doing linear solves? Of course, it will be much computationally intensive. Tac. And so LAPACK is a dense solver, and so in practice, it computes all the eigenvalues. And so we get the full we get the full spectrum of the matrix, but we still get the proper lowest one. So actually, I saw some infinite values at the end, which are probably related to the Dirichlet unknowns. But anyway, these are quite large magnitudes, so not very important, not very meaningful. Okay, and so now we'll try to fetch the values inside the freeframe script.
So
S invert, shift and invert. Yes, because we have a zero shift. So in practice, because it's doing a shift by default, and so a shift try to factorize B. And
B is given by mathematics.
Yes, but just on the boundary. It's an int 1D. Sorry, no, it's not no, sorry, my bad. It's a mass matrix, but we have Dirichlet unknowns, and so for those is rank deficient. It has zeros on all the boundary of the square, so it's rank deficient.
This case is 9, 18 matrix A is non-boundary matrix. It can have the data on the boundary, but the matrix defined by 21 is force degree boundary is 0.
Yes.
So it's a rank deficient. That is trying to factorize from the beginning.
Yes.
It's divided by 0.
Yes, exactly. The null pivot are because of the boundary condition, and so when trying to factorize B, we get an error. And when we switch to
you have the postmodern question.
So no, but if you want, so the opposite way we factorize.
The opposite way is the matrix A is also Dirichlet matrix.
Ah, so you mean opposite way in the sense we shift the parameters in? Okay.
This is the matrix A has the Dirichlet boundary function.
Yes.
But it be factorized.
Yes, with a shift method, it could be factorized. Because again, if we switch, the parameters.
This is my question concerned about TGB.
So
the worst case is data on the boundary is null.
Yes.
Matrix is like null.
But
you said that there's a mass matrix cannot be inverted.
Okay.
Because of the zero data.
Okay. So what you would want is basically to do this.
Could you explain again what is the difference between -1 and -20?
Sure. So
minus 2 is replaced by -1.
So minus
One.
minus 2 is this one.
This one is minus.
Yes.
What is
Minus 20 is a 0 block instead of the identity block.
so that doesn't become clear.
Yeah, and so I will make a parallel, no pun intended, with block systems. So for example, when you have a block system, tac.
If we put most cases -2, but
No, because we don't have the Dirichlet. With a shift equal to 0, it probably works. But with a non-zero shift, we will lose the Dirichlet unknown. We will lose the Dirichlet. No, it actually if we put -2 on both left hand side and right hand side, we'll have spurious modes on all the Dirichlet unknowns. Because we can put so we have basically 0, 1, 0 equal so x equal 0, 1, and so if we put 0 here in x, we can have any lambdas as eigenpairs, and so we get a lot of spurious eigenvalues if we do this.
and this is a set of JJB or 30. We have some trouble.
No,
But
I mean,
here we have to think about the spurious model happens because of the diagonal is 1.
Yeah, so in any case, whether it's -2 or 10 to the power of 30, the important point is that the Dirichlet boundary condition should be imposed on only one of the matrices.
Yeah, sure.
And so if you put here -2, the only way to not impose it here is to put a 0 here.
Because it's only allowed the combination is -20 and 2.
Yes, or 10 to the power of 30
Yeah.
and no on.
And which one?
So I don't like 10 to the power of 30.
No,
We could probably switch things around. It will depend on your it will depend on your A and your B. And so, for example, here the B is a mass matrix. So there are a lot of not a lot, but there are many non-zero coefficients. And so, for example, if we have just a mass matrix on the interface, so just int 1DTH, we would have much fewer non-zeros in in B. And so you want to keep zeros on the diagonal and not put other non-zeros. So it will depend. For putting all the burden of all the computational burden on A. But
for the stability.
for stability reasons, I think it should be the no. Again, it depends if you do invert or shift. If you do shift and invert or shift, because here again, if you are trying to factorize the matrix with a 0 on the diagonal.
If you have a shift invert with 0 shift, or plus 0, you want to put -20
on the
on B.
Yes, exactly, because you factorize A afterward. Yes.
So could you show again what is opposite on shift inverse? We can put something of normalized standard graph or
What's that?
that is you now specify shift inverse.
Yes.
What is counterpart of S inverse?
Just shift.
Just shift. Okay.
So I can give you the top. You can look at page 41 of the SLEPC manual. They are both the shift and invert, and the other one are very seldom used. But yeah, going back to all the -1, -20, -2, and -10, there is also an important use case where we are dealing with block matrices. So for example, if you have something like A, B, C, D, equal, X, Y equal F, J, okay? So if you have boundary condition on A, with TGV equal -1, for example, you need to be very careful with the TGVs on B. And here, B should be assembled with TGV equal -10. Because otherwise, you don't nullify the row of B. And so you basically end up with a system with something which will be 1, and then 1 on the diagonal. Okay, so A, B, C. Okay, so TGV equal -1. And so here you want to put TGV equal -10 to nullify this coefficient as well. So this is something to be careful with. Of course, if you have 10 to the power of 30, then that's 10 to the power of 30, and you don't care about this value. But yeah, something to be careful with the TGVs. Okay, so I think we can use almost the same parameters. So for example, we can use vector, or maybe not exactly the same. I will see vector value. So it's not. Yeah, I'm sure it's not exactly the same parameter, but we should get a rather meaningful error message, I think. So it's not vector. It's vectors. I don't know why I made this stupid switch, but anyway, here we are. And it's not value, it's values. Okay, and so now we can have a look. I will comment out the RPAC values. Okay. And I still need to switch from invert to shift invert. And I can do this, I think, using the S params. So just as for the set in the previous, for the KSP, I can do also S params here, S params, ST type, S invert. What's that?
I mean, so your TP is solid, you don't have an object which you can solve.
For the ST, no. But for example, you can do something like set C S params PC type hyper KSP type FGMRES. And so then SLEPC will use hyper and FGMRES.
Yes, but you can specify the parameters related
to the APS? Not to this day. Yeah, this raises a critical issue, let's say, in the sense that in plain PETSys or in plain PETSy 4Pi or whatever, there is an object which is called EPS, yes, on which you can set the parameter. And in FreeFEM, we have made the decision of not exposing an EPS and just let the user call EPS solve and create for the user the EPS inside EPS solve. Here we can use, I don't remember, you can use prefix. So for yes, so for example, I think we can do prefix my eigen problem, my EV problem, and then we can do my EV problem ST type, and here we can do. Okay, so this is wild. I've never tried this, so there is probably tag my PC for ST, and so attack yank for tac, and so let's do.
You have an underscore in my EV problem. Yeah.
Ah, yes. Thank you.
But not in between my EV and problem. The first.
Ah, yes. Okay. Thanks. Okay. So there is. there is, okay, let's try. No foul, no harm. So none of this is necessary anymore. And so let's do my EV problem, EPSU, my EV. Okay, K does not exist. Int, okay. Okay. Okay, so probably not what we want. Tac, tac, tac. Okay, so the good thing about PET-C and SLEP-C, I mean, of course, it's better to make no mistake at all, but hopefully in PET-C and SLEP-C, when you have an error or when you make an error, the error message and the backtrace is clear enough. And so here we are seeing that the option prefix should not begin with an hyphen. Okay, and so basically what PET-C and SLEP-C is telling me is to remove this and this. Okay. So still an error, I think. Oh, maybe not. So am I making the right things? Okay, so tac tac. Let's again go back to so my EV problem. EPS relative error ASCII info detail. Encore, je me suis trompé. So am I computing the right stuff? For the first one, yes, but I changed something. S invert. So of course I need to compute more eigenvalues. So okay, I will do prefix push and prefix pop as yesterday. Prefix push my EV problem. So I don't think I need an hyphen here. Prefix pop. And so then I can just remove all this, and that's about it. And so what I want is EPS NEV plus NEV. Okay, so why am I getting ones instead? Did I change something? Ah, yeah. So here you can see the spurious values on the square. And so I need to go back to 10 to the minus 20, sorry. And okay, better. Tac. And so we have the same, so not exactly the same 20 eigenvalues, precisely the same. Keep in mind that we are computing a space spanning the first 20 eigenmodes, and so we may have linear combination or slight variation, but we can see that the eigenvalues, not the eigenvectors, the eigenvalues are precisely the same as with RPAC.
So the occupancy is now class 8.
Yes, this is the
default is the direct. So or is it tolerance is defined by the default of the case?
No.
No.
This is the tolerance of the EPS. Yes. So the eigenvalue problem solver. So here I'm using an eigenvalue problem solver, which is solving linear systems, and I'm solving the linear system iteratively. Yes. And so there is two tolerance, one from the EPS and one from the KSP. And so I can change these, in fact. And so, for example, I can try to have like a looser tolerance for the inner solvers. So, for example, my PC for ST, KSP, RTOL 10 to the power of -2. And I can have a tighter tolerance for the eigenvalue problem. So, for example, EPS TOL 10 to the power of 12. Okay, so what this does, it's not a good idea, but anyway, we'll try it, it solves the inner linear systems less accurately, but we want a better accuracy for the outer eigenvalue problem solver. Okay, usually it's the other way around. I mean, it's this way. It's not. It does not make much sense, but it should work. And so, am I using the? So the tolerance is lower, but we can actually see that we have not so much increased the quality of the eigenvalues.
So we didn't take it into account. I have explained the same.
So probably we need to increase the tolerance of the inner solver. So if we go back to 10 to the power of minus 12, for example, is it any better? Yeah. So yeah, this is a lot of knob turning. Yes. Of course. So there is no error because so that I mean, you have to be careful about what you qualify, what you say is the tolerance. And so, in fact, so this is one of the parts I'm the least familiar with. So if we go back to this, let's say, dumb parameters, if we do EPS monitor, sorry, I think it's my EV problem underscore EPS monitor. What does SLEPC tells us? It tells us that I'm guessing the error is absolute, whether here we display the relative error. So we can see.
It's not six orders of magnitude.
Let me check.
But I didn't investigate, but I've seen this.
Sure.
Not reaching the tolerance.
Okay, you were right. So, okay. Let's have a look at the monitor. So can we check? Okay, so absolute error convergence test, relative. So probably if we play around with one of those parameters, we could get what we want. So maybe if we try this, tac. Ça commence à me saouler ce chat. Ça marche. Non, shoot. C'était quoi? C'était conv. Alors, on a real et norm. OK, donc on va tous les essayer. Apps. OK, apps, conv. Ah, okay. Yeah, so the thing is that it's checking with respect to the least converge eigenpair. And so here we can see that the error for the least converge eigenpair is 10 to the power of minus 12. And so I'm not sure I can tell you computed matrix norm. Pop. I don't know. But yeah, in any case, it's difficult to link all the tolerance together with respect to the inner KSP tolerance if you're not using an exact solver and the outer solver, outer eigenvalue problem solver. Probably it's best to look at those with an exact solver. In fact, this is we are mixing all the concerns together, so it's probably best to do this. Tac. In fact, the problem is symmetric, so we can do a Cholesky. And so now the things are looking like we want. So probably avoiding mixing concern is a good way to.
Then you have a small eigenvalue.
Okay.
Problems, you have a small eigenvalue. And
Okay, so maybe we can try this on. It should work. So basically, we have no eigenvalue, no boundary condition, so a purely floating domain. Okay, so maybe.
yes, here you are. Yes.
So TAC, we probably want to switch to something slightly more robust. So let's do mumps. My PC factor math solver type mumps. Okay, and so you're talking about those ones, those errors.
In this setting,
Uh-huh.
You define the normal matrix,
Yes,
and that is inverted, right?
this one, it's not invertible.
No, no, which part is inverted? So, like,
This part, this is still this part which is inverted.
No, now you select the shifting inverse,
Yes,
the CFC expression.
yes,
In this case, A is should be factorized.
yes,
So what it is, the theoretically is not inverted.
yes,
And mappers may try to do some inversion,
yes.
but no accuracy. So we got the wrong result.
I mean,
Right?
they are not so wrong, let's say.
But
It's symmetric when you have again.
it's the same
Yes,
because
so I think this is because the problem here is not.
it's not obvious.
Yes, but we are not forcing the problem to be symmetric, in fact, here. So I need to force this to be my EV problem, EPS, gen, Hermitian. So now I don't have any complex eigenvalues.
Sorry, what do you need now?
What are you?
I'm confused. Sorry.
No problem.
Without your last modification,
Uh-huh.
is CFC try to compute of the eigenpairs
Uh-huh.
in complex vision.
No, in real, but we are not saying that the problem is symmetric.
That means all computation done in complex.
No,
Anyway,
the computation. So again, SLEPC, PETC are in C, and so here I'm doing things in real, and so everything is done in real precision, in real with real scalars. But we are not saying that the problem is. We are not forcing the eigenvalue problem solver to use an algorithm for symmetric matrix. And so the theory of symmetric real matrices tell us that we may have complex conjugated eigenpairs. And so because
that's okay, but you something here.
yes, to force the problem as symmetric. And so now the algorithm which is used by SLEPC ensures.
This needs to be symmetric. Matrix is symmetric diagonal.
Yes.
So you choose the symmetric eigenvalue solver.
Yes.
So the prediction again of the command, so we fix those.
No, that's fine.
Yes, this is gen Hermitian.
Uh-huh.
But this is not real. I'm very confused.
Okay. Sorry. Sorry. Hermitian means symmetric in real and means Hermitian in complex.
But very bad names. Okay, so in this case, is the Hermitian is suppose for eigenvalues is
Real.
real.
Yes.
So that is even matrix is complex.
Uh,
So the complex matrix is if that matrix is again,
uh-huh.
you have the diagonal entry.
Yes.
Everything is
Yes.
real.
Yes.
That's not. So then there's a only question is here is used purpose.
Uh-huh.
And but the error is very also excellent. Previous comparison we saw the AX minus B. Oh, this is relative. No, this is not relative.
Yes, we can check the relative one.
Absolutely not. In that case, you got it will be better.
But it's still higher than the tolerance. If I'm not mistaken, it's still 10 to the power of, yeah, much higher. But
anyway, the numbers need something good stuff, even that matrix single.
Yes, but
So if you change the numbers to standard.
Yeah, so I actually shell mode, okay.
Sure.
Where okay.
That's not it. Type solo types.
Oops, sorry. I don't know. Again, it's the magic of eigenvalue problem solver. I don't know, but it's the same with RPAC, with LEPC. I don't know. Those matrices are not supposed to be invertible, and yet the linear solver are inverting them with no issue.
If the pivoting is good, maybe we don't need to compare about that.
Well, Scholmod does not do any pivoting.
That works fine.
I don't know why.
But in this case, can JMS works?
As inside the inner solver, like doing iterative refinement.
No, just starting from zero.
But with what preconditioner?
Literally, because I don't know the block space is surrounded by image space. Okay.
So
in this case, we can make some of the quasi version.
Well, for example, I think in this scenario where A is not invertible,
Yeah, sure.
I think if we put something like hyper, it will not converge. Maybe I'm wrong. This problem is not too difficult, so yeah. But for sure, the error is much higher. Let's see the inner my KSP convert reason. Okay, so yeah, I think this problem is a little bit too easy for hyper, for Boomer RMG, and so even if it's not definite, the multi-read solver solves it, no problem. So maybe with GMG, no, it seems to be it's struggling a little bit more, but it's still fine. The residual is perfectly fine. So yeah, there are a lot of ingredients involved, and so
that is very interesting because we can select all the some combinations
Uh-huh.
in the solver.
Yes.
And also we can assume the outer solver of the eigenvalue solver based on the Hermitian or general matrix.
Yes. You're welcome.
Can you just show the inner residuals again on the left lobe? You see the first ones are bad.
Yep.
Lowest mode is not computed. Okay.
Then the second.
Yeah, so
Okay,
it
just affect the first one.
So we can.
Considering these bad first solutions are affecting the whole.
Also, this is strange.
Shoot.
Other process is the starting from platform. That's one is not good. That's one is let's say it's good, so it's too much better.
Yeah, but again, the problem is in the. Okay, so here this is interesting. I think we see the indefiniteness of the problem because the residual norm is decreasing, but we see that the true residual is stagnating. And so I think that the first wrong solve is basically the eigenvalue problem solver, which is picking up the null space of the problem. Because we should see just the same decrease in residual norm as in I mean, the true residual norm as the unpreconditioned residual norm. So, yeah, exactly. This is very interesting. We see that for the other solves, the true residual norm is the same as the unpreconditioned norm, but for the initial problem where we have not picked up yet the kernel of the matrix, they are completely different, and so, good stuff. And so once we picked up the kernel, then the residual are okay. So this one is garbage, but afterwards I think it's perfect. Yeah, okay.
We have 6 panels.
Yeah, so the 6 first solve will probably be garbage. So one thing that we can do, in fact, is add a deflation space to EPS solve. So I think it's here. Oops, sorry. I think I added the interface. So foo égale bar int bar. Yeah, there is this deflation parameter, which can probably be used to remove the null space. But I must say I've not benchmarked this parameter very much, and I'm not sure it's working as it should. So
another possibility. Now is A is defined by the compact person. You create a knowledge. How about to add the relevant modifier? What's the solution in the
will you get the same eigenvalues?
Because of the concentration, we know the zero eigen. It's definition.
Yes.
If you introduce already the in interface, but that's by hand by them. So now it's already how we want to say. We can extend.
Sure. I mean,
not easy, but I will check this.
So I'm not sure it will.
It's not. Okay.
We can try to add it. The thing is that
in that case, is we have to define the regular divider.
Yes.
And so size is one size bigger.
Yeah, sure.
It will be complicated.
No, I mean it does not change much. We can try. We can try. So I will. I just wanted to make it parallel as well after, but we can just add the matrix. So it shouldn't be too complex. We need a new varef tac. So varef C, and so then it's tac. Then we can do real int Lagrange equal C of 0 VH. Okay, so this is interesting because we exactly end up in this scenario. And so we actually, no, we don't have Lagrange multiplier here. We don't have Dirichlet boundary condition, so it's fine. Tac, tac. So it's int 1D on the boundary, for example, or on the full domain. I mean, it's fine either way. Then we have L, and so we can do something like mat nest of C, which is, so C, L transpose 0. Then we do mat ND, which is D 0, 0, 0. Here it's probably 1. No, wait. No, it's 0. Tac. Wait. So here I need to put real. So interesting problem here. Okay, so I will put this here. So here in this line, so basically when FreeFem has a block matrix, it needs to detect the number of columns and the number of rows of each block. And so the problem needs to be well defined in the sense that prefem or PETSI needs to be able to know the size of each block. And so here, can FreeFem detect the proper size of this block? The answer is no, because we can have we could have, for example, 2 columns of zeros and 2 rows of zeros here. So we'll just put an alpha here, which is 0.0, and I will put alpha. Okay, FreeFem / PETSI and or PETSI needs to be able to deduce the proper number of rows and columns of the 1-1 block, which is not possible with zeros everywhere. So use a single scalar to force the dimension to 1.1. Okay. Tac. Okay. And so let's cross our fingers, I guess. So it's not C, it's NC. It's not a EPS solve NC and C and D, it's NC and ND. And of course, now we have a vector which is slightly bigger because it has a single additional rows more. And so we cannot use an FE space anymore. And so we need to switch to a row array. And so we can do, I think, real int row v of dimension vh.end of +1 nev. Okay, and so now it's not vectors here, and it's not EV, so it will be row EV, and it will be, I think, row vectors. And no foobar anymore. Okay, so I will comment this out and I will switch back to exact LU factorization or Cholesky pre-only. And so next, I want to extract all the rows of row EV inside EV and just suppress the last row. And so I can do this with the standard FreeFem syntax. So row EV of I equal 0 vh.end of -1. What's that? Bracket? Here. Yes, thank you. No. No. Yes, okay, sorry.
That's okay, but we don't need to write it. That's directly the kind of the double quotation syntax.
This one?
Oh, yeah.
Yeah, it's much faster than doing a for.
Yeah.
Yes, it should be. For some types, sometimes it's not there, but we can add it. Okay. I'm not sure of what to expect. Really. Il y avait un problème?
Because it's not an array of vectors, it's a matrix, and I think the syntax is wrong for the extracting a column.
Yes, you are right.
And then parentheses.
Something like
I know I.
Yeah.
Maybe you can't do it.
Okay, let's try. We probably have other errors anyway. Tag. I don't want to use shoal mode. Okay, unused parameter. It's not row array. Okay, sorry. Row vectors. Row vectors. I think it's in eigenvalue, in fact. 83. Okay, so this is wrong. And so, yeah, okay. So this is what you mentioned earlier. Tac. So all the rows of the ith column. Does that work?
That's right.
Ah, okay, so it works, but there are other issues. Okay. No non-zero submatrix in row 1. Okay, so comment? Le L, c'est un. So L is a real int, and it's perfectly fine to directly put a real int inside the mat nest. You can also put real int. And so here, okay, this is interesting. I'm doing some check inside the PETC plugin, I think, whether this value is 0 or not. And if it's 0, I just don't insert the value. And so I think I need to put a small epsilon. So here we can see no non-zero submatrix in row 1. And so I will try again. No. No. Okay, so again, we try to provide comprehensive error message. And so here we can see that, so we are using a matrix defined by block. Again, block matrices are nests. And so we see that we are using a convergence parameter using the norm of the matrix. But when you are using a mat nest, we don't have the representation of the global matrix. And so in practice, it's not possible to compute the norm in PETC of a matrix defined by block. I'm not sure why it's not implemented. I will try to add that later on. But anyway, I think if we remove this parameter, it should be better. Tac. Okay, so it's doing something. Is it doing the proper stuff? I have actually zero clue. But we go back to the okay, so I think I'm okay. So it's probably not possible to copy it like that. Oh, out of bound, il F baserait. Intéressant. F baserait, il est où le F baserait? Wait. Line 96. I want to get this to work. I need to figure out what's going wrong. Yeah, the value are perfectly fine. That's why I want to make things work. So am I plotting U1? Oops, sorry. Attends. EV, c'est quoi ça? On plot. Yeah, I don't know. So we get everything but the singular, but the zero eigenmode, because now the problem is not indefinite anymore. We have the proper constraint. The problem is definite because of the Lagrange multiplier.
Error of this one is starting from constant is not 0.
No.
It detects of 1. And then this corresponds to the new corresponds to 0 eigenvalue.
So there is no zero eigenvalue anymore since the problem is definite.
Yeah, but it's government there.
Yes.
It's us, you're picking up some opposite.
Right.
So the other value is
They are the same except for the first one, which was previously 0.
maybe we can think about how much part of something defined, but here is a matrix is invertible.
Yes.
Definitely we can have to meet
Right.
but since the different values we are so we saw previously.
I think they are rough. I mean, yeah, maybe there is a small variation. Yes, probably.
This is a big so 5.08.
What's that?
5.08.
For the eigenvalue?
Yeah.
You mean in terms of tolerance?
Another case by using numbers. And that is was not was on 0, but after value between 30 single.
Okay.
I don't know if it was. This can say the singularity of the matrix.
Right. Yes.
I think the reason is that you use kind of L
Yes.
comes from the binary form.
Yes.
It's not complete one.
No. No, it's
That is the if we eliminate of the kernel A, we have to find one vector. So
we can put one if you prefer vh.end of and then L equal 1.
that case seems to be different, right?
Actually, I want to try whether this works in the plugin. Wait. Probably. Oh. Okay, I think I've detected a bug, but anyway, we go back to L. And so we still have the first one, which is 1.
The first one is valid, okay? But no, this first one never becomes 0 because
The matrix is not definite, so there is no 0 for sure. Okay. So of course, one thing which is nice is that you should also be able to go back to RPAC if you ever want to. And so I think you can just do EPS type RPAC. So my EV problem, EPS type RPAC. And so now we have indeed solving the problem with RPAC instead of the Krylov-Shor method from SLEPC. But here, as I said, the default Krylov-Shor method is just the same as RPAC. So the eigenvalues are the same, I think. Yes, they are the same, but we don't get the eigenvalues in the same order, or we just get linear combination one of the other, but the algorithm are not the same, but obviously they are not implemented in the same package, so it's not exactly the same. And that's one thing. So RPAC, Krylov-Shor. And maybe just to wrap things up, we do things in parallel. Yes. Yeah. So these are the okay. So so what I've just recently discovered, that can help things, is not to change it; it's to always do orthogonalization. So the block of active vector in the Krylov-Shor method is not always necessarily orthogonalized and so on and so forth. But there is one parameter, I think, which is so BV in SLEPC stands for basis vector, and so it's BV orthog refined to set to always. So if you know a little bit about Krylov methods, you know that with Gram-Schmidt, sometimes you have a lot of orthogonality, and depending on some scalar product that you can evaluate cheaply, you know whether you need to do iterative refinement of the orthogonalized basis. And so in PETC, in PETC and in SLEPC, there is a mechanism to detect whether the basis must be re-orthogonalized or not. But I've just found out that in some case, the criterion is not, I mean, it says that the basis should not be re-orthogonalized, whereas if you do it always, the method is better in terms of accuracy. And so, so for general eigen problems, for example, mostly for the saddle point solver, in fact. But anyway, you can force the orthogonalization, and so it's instead of if needed, it's always. Okay, but yeah, these are the kind of parameters that are difficult to tell you beforehand. If it will help your solver or not, but it's the kind of knobs that you can play around and that are actually quite easy to adjust in SLEPC. But if you want to do the same in RTAC, you can't. You need to rewrite RTAC basically. Okay. So maybe we try to make it parallel. So for the parallel one, I will Lagrange. So I will go back to a version without the Lagrange multiplier because it adds a lot of bookkeeping for which is not very interesting, I think. And so the code without the Lagrange multiplier, we were using the finite element space, Cholesky, no preconditioner, just the Cholesky, not the EV, and then we do EVI. And then we plot U1, so this is perfectly fine. Okay. And so instead of ND and C, I go back to C and D, and we don't forget about the Dirichlet boundary conditions, TAC and TAC. So just making sure that things are still running. So encore TAC, ligne 19. Sorry. Hop. Hop. Okay, so back to the original problem without a null space. So there is no zero as eigenvector, as eigenvalue. And so now we want to make the code parallel. And again, there are many ways to do it. I will do it using the lightweight macros from include macro ddm.edp. Okay, and so the thing that we need to do basically is to break down the mesh TH and to build a distributed finite element space, just as we did yesterday. And so we can do that in two steps. For example, dmesh create of TH, which will be in charge of spreading the domain into small subdomains, and then creating distributed matrices. So I will need one for the left-hand side, it was called C, and one for the right-hand side, D. Okay, and so I can just do, so we are using a P2 finite element space, and I can do mat create on TH, one for C, and one for D. Okay, and so now what needs to be changed? Here we are using the same varefs. Of course, we don't need this anymore, but it doesn't hurt to assemble them. wait, does it hurt? No, it does not hurt, but we need to feed those matrices into the previously created distributed finite element space. So C and D here. And so the notation is slightly different. So sorry, these were the Lagrange multipliers, so we don't care about this. The notation is slightly different. So we have already created C, and so instead of using the constructor operator like in C++, we just use the affectation operator, and so we can do C equal A, I think. We will double check, and we do D equal B. Okay, so basically we take the sequential free-form matrix and we put it inside the distributed PETSI mat. And then nothing should change. We are still using Cholesky factorization, but this time in parallel. We are still using shift and invert algorithm, and we still want SLEPC to compute the relative error and so on and so forth with some prefixes that we have set previously. The same remains the same. And the rest remains the same, sorry. And so instead of plot here, I want to do a distributed plot, or I can just use save VTK, for example. So save VTK, save VTK of eigenmodes dot PVD, dot VTU with the mesh, the eigenvalue U1, the data name eigenvalue, the order, FF order, and I want to append after the first iterate. So if I greater than 0, true, otherwise false. And so FF order, oops, sorry, I put this in the middle, tac. So FF order, this is a P2 function, but I'm just doing the output in using P1 function. That's perfectly fine. Okay, so let's try this. So first in sequential, always good to run things in sequential, even if they are supposed to run in parallel. Okay, no error. Let's see some eigenmodes on the on disk. So let's have a look. Eigenmodes.pvd. Okay. Wait, this is not order one. Sorry. Oh, that's a bug, I think. I think that's a bug. Anyway, eigenmodes. Okay, let's go back to running things. Freefem plus MPI. Okay, we reload the files. Shoot. Okay, now it's P1. Okay, good enough, I think. Okay, perfect. And so now for the real test, let's run this in parallel. FF MPI run 4. Okay, so I have an exact assert. Why is that? So things are running. I think it's a bug. I think I'm forgetting to broadcast. What is NR? Okay, let's forget about the assert. There is probably some control variables which is not assigned on processor other than 0. So let's just rerun everything. Tac with for process. And so tac. Sorry, I think now it's eigenmode underscore 4 because I have 4 processes, so 4 subdomains. Okay. Okay. And so we have solved the eigenvalues of the Laplace operator in parallel by just adding 2 lines, 3 lines, 4 lines, 6 lines of code, basically. And so, yeah, just as before, we can leverage the flexibility of PETC and SLEPC. So for example, we can do stuff like my EV problem, EPS view mat0 draw pose -1 geometry, no, draw size 100, 100, 100, I think. And so here is the sparsity pattern of the matrix. So this is so mat0 is the left-hand side matrix, and so we can do the same for the right-hand side matrix with yank2 with mat1. Okay, so this is the left-hand side matrix, and yes, and this was the right-hand side. I'm not sure why there is the same number of non-zeros. Okay, maybe if we do something like int1d, except that this problem is not well posed. Why is that? Okay, so now we have fewer non-zeros. And so, of course, we don't have the same eigenvalues. But I think you get the idea. Do we loop? Don't we? Are they the same? So I'm not sure actually at the. No, okay, there is an issue with the convergence of the solver. This problem should be well posed. Why is it not converging? No, but it doesn't make any sense. int1d just integrates on the border, but here I'm using on directly boundary condition everywhere. So this is stupid. Maybe if I do something like just boundary condition on part of the domain, it will be better, but I'm not sure. Tac. I think there is no infinity anymore. Okay, so things are slightly better. I'm not sure if it makes any sense. So, but anyway. And so now, okay, now the eigenvalues are different. Tac. Questions? Yes.
Internal solver
Yes.
should be distributed.
Yes.
In this case, they use specified units. Yes.
So currently I'm using LU, but yes. We can go back to yes, the type is mumps, but we can try to go back to hyper and
the LU is specified. Actually, the distributed mumps are before.
Yes. Yes, so keep in mind that in PETC there is no distributed LU solver by default, and so you need to have something like download mumps or download super LU dist or download stream pack or download MKLC Paradiso. Au revoir.
So the LU that is accepted, LU default the solver of LU is now restricted numbers.
Yes.
But,
so if so you can see that okay, so
LU, but message source type with LU.
Yes.
Actually is running with functions.
Yes, this is because so LU is the type of preconditioner or the type of factorization that you want to do. So you can do either LU or Cholesky, and then you are free to use whatever what is called a solver package to perform the LU decomposition. And so, for example, you can do st. What is the name again? The prefixes are terrible. They are very painful to remember. So myPC for st, myPC for st, myPC for st. And so then you can specify what package you want to do to perform the LU factorization. And so you can use, so it's PC factor, math solver type, cuckoo. And so here I should get hopefully meaningful error message. Could not locate solver type cuckoo for factorization of type LU. Perhaps you must configure with download cuckoo. Okay. So of course there is no cuckoo, but if you do super LU dist, I'm not sure I have it installed on my machine, but we will see. Ah, I have it installed. Okay, so I have it installed. I don't have, for example, strumpack installed. So if I do strumpack, I should get again a meaningful error message. Okay, could not locate strumpack. And so in PETSI, you can do 4 types of factorization. No, 5 types of factorization: QR, LU, Cholesky, ICC, incomplete Cholesky factorization, and incomplete LU. And so, for example, if you do ILU with mumps, it should throw you an error message. Again, something meaningful, hopefully. Math solver type mumps does not support factorization for ILU matrix. And so you can add so it's extremely flexible in the sense that you can have inside, for example, the PETSI plugin in FreeFM, a new solver being registered automatically. So you can add new solvers that are not necessarily in PETSI, but that are registered after PETSI has been loaded.
The user can change the command line balance.
Yes.
Can you show again the flag to specify the solver package on the...
Yes. So ST, it's a PC factor, and then math underscore solve underscore type. You mean take a photo? Yeah.
Usually I only play with the case. So
right.
Don't think about so much about the
Sure.
Sometimes it's important to play directly to not distribute the things.
Yeah, sure. Yeah, and so for example, in fact, if we go back to your initial question, if I use the same program but with a single process, it will use PETSI, I think, LU factorization. Oh yeah, forget about this flag. Tac. And so no. I think it's, but do I have mum somewhere? Yes, I have mum somewhere here. Sorry. So let's forget about this flag for a moment. So by default, I'm using the PETSI LU factorization. It's not written, but yes, package used to perform the factorization, PETSI. And so you must be careful, for example, because you may want to force mumps in sequential, I mean, with one process and with multiple process. So it usually doesn't hurt to put always the flag PC factor mumps such that it's using mumps both in sequential and when you are running things in parallel. So we have about 17 minutes left. There was initially a question with respect to SNES solve. So it's a little bit it's a little bit of a mouthful, so maybe I will just go through one of the examples using SNES solve, because if I try to start from scratch, it will be the likelihood that I fail in the 17 minutes is quite high. So I will just, so I think it was Jules asking the question, and so Jules is a frequent participant in the Monday session at the end of each month. And so maybe we'll go into greater details with the SNES solve next time you join, if you join. But anyway, for those who don't come on Monday at the end of the month, I will just go through an example using SNES solve. They are inside example HPDM. So the name of the folder is not very. It's not the brightest because now most of the examples are PETC related and not HPTDM related, but this is for historical purposes, let's say. And so I think if we go at the bottom, we have a list of problems. And so you can see the list of linear problems. And you can also have a look at the list of non-linear problems. For example, there is a simple one, not too difficult at least, which is a Bratu problem in 2D. And so if we go inside that file, so we see a bunch of code for defining the geometry. It's a simple circle. It's a square, sorry. And we are using P3 finite element. So keep in mind that when you are using Lagrange polynomials of order higher than 2, you need to load an additional plugin. So there is element P3, and I think there is also element P4. I don't think we have P5 and higher, but if some of you need it, please ask us. And so the main thing that you have to keep in mind is that when you want to use SNES solve, or in fact also TS solve, you basically to provide to PETC two functors, one which will be used to evaluate the residual of your functional, and one which will be used to update the Jacobian of your nonlinear problem. So in this example, so the varef is here. So I think it's in fact the math is derived in the tutorial. If you want to have a look, I think. Let me just have a quick look. Paraview, it equation. Sorry, it's going a little bit fast. No, where is it? Where is it? We are getting there, don't worry. Up, here we go. So if you want to have a look at just the mathematical derivation of the Jacobian and the residual function, you can have a look at the FreeFM tutorial that I mentioned earlier, and it's the example number 4. And so this is the problem that we are solving. We can get the residual function and the Jacobian quite easily by hand, let's say, and we end up with such varefs, so one for the Jacobian and one for the residual. And so we can provide two functions, one for computing the residual of the function. So the output parameter is a vector, so a real int, and one for updating the Jacobian. And so the Jacobian is the same math throughout the execution of the nonlinear solver. And so we just return an integer, which is an error code. So basically we return 0, except if there is a failure, in which case we return something else than 0. You can put 1 or -1 and or whatnot. And so now what will happen basically when you do SNES solve is that PETC will perform a couple of operations, and whenever it needs to update the Jacobian, it will call the funct_j function inside the FreeFM code, and whenever it needs to evaluate or compute a residual, it will call the funcres. And so there is back and forth between PET-C and FreeFEM, and it's completely hidden to the user, but keep in mind that those functions, funcres and funcj, will be called over and over by your PET-C, who is in charge of doing all the Newton method. So there is no for loop for doing the Newton method. It's automatically done for you by FreeFEM, which will call those two functions back and forth. So I will just run the program. So I go, for example, here, repo freefem source opt. So git diff. Okay, so the file is clean. It's exactly the same as on the repository. Just double checking, but yeah, okay. So for educational purposes, I guess, am I doing the same on master? Okay, so for educational purposes, I'm using a domain decomposition preconditioner using exact inner solver, so sub PC type LU. Okay, and so now we can have a look. For example, if we run this with for process, let's say, tac v0 with graphics. Okay, so we get the solution in a distributed way. So this is the solution of the nonlinear problem. And we get all sorts of information. So we can see that the Newton method is not converging very fast. We may be able to switch okay, so it's a Newton with trust region. I think if we use a line search, it will be slightly faster, but I'm not actually sure. SNES type, Newton with line search. No, I think we need to wait. Give me one sec. SNES. Okay. I'm forcing trust region on the S params. So whatever is inside the S params take precedence over whatever is on the command line. So something to keep in mind. So line search. Is it any better? I'm not sure. It's been a while since I ran this problem. Yeah, it's much better. Tac. So yeah, we can see all sorts of statistics. So you have, of course, the norm of the residual. You have some statistic with respect to the line search method. So I think that the line search that we use is a backtracking method with cubic interpolation. So there are so many methods in PET-C that it's difficult to have a clear overview of the full package. But there are many tutorials available on the web and on the manual as well. For example, I think we can switch the line search method. So let me go to the PET-C documentation. Let's look at SNES line search, and instead of a cubic one, let's do something like let's do basic one, for example. So instead of backtracking, let's do basic SNES line search basic, and it works just the same. So of course you can also control the norm of the nonlinear solver. You can control the norm of the inner linear solvers. And so, fun fact, there are some finite element packages that are using SNES, so the scalable nonlinear equation solver, to solve nonlinear problem. Because a linear problem is just a nonlinear problem with the Jacobian being A and the residual being AX minus B. And so the thing is that the default tolerance for the nonlinear solver is 10 to the power of -8. And the default tolerance for the inner linear solver is 10 to the power of -5. Okay, and so sometimes it happens that when you solve a linear problem with a nonlinear equation solver, it takes more than one iteration just because the relative tolerance is not the same. Okay, and so there are people that are saying there is a bug in the nonlinear equation solver. There is no bug. It's just that the residual is not the same. So this is something that that happens sometimes when you are not careful with the tolerances. But yeah, for example, in the SNES solve, you can have access to the total number of linear solver iterations. So basically the sums of the KSP solve iterations, so 27 plus 29 plus 29 plus 29. You can have the number of function evaluations. So depending on the type of line search method, so if you do backtracking and stuff like that, you can have more function evaluation than Jacobian update and so on. And so there are all sorts of statistics available to the user. And so to get this, I guess that you have an idea of what to use as a parameter. It's of course SNES_view. Keep in mind that all the PETC viewers, all the SLETC viewers are something like SNES view, KSP view, EPS view. So for example, we can also add SNES view with KSP view. And so it means that at each linear solve, we'll have a view of the KSP solve. Why don't I get KSP view? Is there a prefix somewhere? Huh?
There is a KSP object.
Yes, so maybe on the I guess I need to call KSP set from option. So small technicality, but anyway, if you put KSP view on the command line, anytime there is a KSP solve, you can get the properties of your KSP object. And so here we are using GMRS with an additive Schwarz method, with an overlapping Schwarz method, with an amount of overlap of 1. Yada. So I'm sorry, Jules, it was quite fast, but we can talk more in greater details about SNES solve maybe on the next Zoom session, the monthly Zoom session. Yes?
Definition of the Jacobian.
Definition of the definition of the Jacobian.
There are problem about homogeneous one, original one.
Ah, yes, yes. The Jacobian must have so keep in mind that in FreeFM for the Jacobian, the value that you put here has actually no impact whatsoever. So if you put 1, 2, 3, 4, 5, it's always the same.
Just by replace by derivative.
Yes. So the value is important for the residual. For the bilinear part, not for the bilinear part. For the bilinear part, we don't care about the value that is here. You can put. What is important is for the linear part, and so for the linear part, the residual with respect to the to the homogeneous, yes.
So sometimes if we work with a nonlinear program,
Nonlinear, yes.
It shows kind of the method to update the parameter. So is the line search
Yes.
or plus region.
Yes.
Is some report could be we can see if this is the SNES view.
Yes.
Or some parameter maybe kind of return value to the homogeneous or something.
Right. Okay. So yeah. So I will end up with this. I think. So inside the plugin, plugin MPI PETC code. So for most operators, like KSP, SNES, TS, we have a parameter which is the converge reason. And so you can get the converge reason, and so you can get a value whether the KSP, for example, has converged because the relative tolerance was lower than the threshold, or the absolute tolerance, and so on. So I know that there is the KSP converge reason for the KSP. I think it was added for TS, and we also have it for the SNES solve as well. So I think we can add something like reason equal rs. I think this is stored as an integer, and so then if you run this, if you run this and you do C out of rs, you should get, maybe I will add some stuff like SNES converged reason equal tac. Then if you run this, you get something like SNES converged reason equal 3. And so now a little bit of gymnastics. You go inside the PETC documentation, you look for SNES converged reason, and you get that SNES converged reason 3 means that we have converged because the F norm in relative tolerance was lower than the tolerance. So yeah, PETC use error codes and use converged reason and whatnot. And so unfortunately in FreeFM, we have not exposed those types directly inside the grammar. And so we took the easy approach of returning integer. And so instead of an error code, you have the integer. And so then you need to look at the PETC or the SLETC documentation to make the one-to-one correspondence between the integer and the error code or the converged reason and whatnot.
But that's not enough to just mathematical understanding somewhere. So this is defined by code 51. We don't need to look for us. Maybe we can choose another stuff. Of course, it's a reason. Of course, it's less converge. But in the case of the some, if the problem has no solution or higher level number, we can change the study.
Yes. Yeah, if you get something like a return code which is lower than -1, you can, for example, go back in time in your iteration and change the continuation parameter, and so not increase the Reynolds number so much. And so it's actually one of the big strengths. The error code can be used to adapt to make your simulation more dynamic and make sure that you are converging. And if you are not converging, try to adjust it so that you know what you do, you know what needs to be done to make it converge, like decreasing the mesh size or decreasing the Reynolds number, and yes. So for example, you can check whether there is an inner solve failure in the KSP or if the lines are... Yeah, exactly. Yeah.
We have to think about it.
Yeah, exactly.
We can use this as the fundamental.
I mean, yeah, everything can be written with a, I mean, a lot of things can be written with a SNES. Okay, so I think it's time to wrap things up. So whether you are on Zoom or here, thank you for being there. There is just a reminder that every last Monday of each month, except this month, there is a Zoom session open to everyone. There is no bad or stupid question, and you are free to welcome with your problems, and hopefully we'll be able to help you out live. And the Zoom link is usually posted by Frederic on community.freefm.org, and you don't need an account to access the post to get the link. So even if you are not registered, just go to community.freefm.org and tac, I will just show you what it looks like. It's English, but written by Frederic, but you should get the info quite easily in any cases. Zoom session, I think. Zoom, no, not this one. Zoom discussion session. And so, yeah, you get the Zoom link and you should be good to go. So feel free to join us again next month. I will stop the broadcast for people on Zoom. Thank you for joining and see you soon. Thank you.